And we're back. We're looking at chapter 3.2. Very exciting. It's going to be about exponential growth and decay. I mentioned it earlier about growth and decay, exponential growth and decay, and how to identify it. But now we're going to put a little more math behind it and understand what it means as far as how much growth you're having, how much decay you're having in this exponential growth or decay. Okay, so let's go to a new page. And our exponential growth model is, oh, that is the wrong pen. That P of t, population at time t, equals the initial population times 1 plus r to the t. So this is the initial, oops, go down here. Initial population at t equals 0. So if t is equal to 0, this whole thing gets turned to 1, and we just get p0. Okay? And r is the rate of increase or decrease. It's either one. So we're going to write it in terms of 1 plus r. Okay? So if r is greater than 0, what do you suppose that means? That means exponential, the suspense is incredible, growth. And if r is less than 0, so if it's negative, then that means we have, this is a hard one. What do you think it is? Exponential decay. Yeah. Okay. This is, oops, stop that. This is what we're going to use all through this chapter about doing exponential growth and decay and figuring out the rates at which we're growing and decaying and predicting what populations will be at certain times t. Okay? So keep this. You want to have that somewhere when you're working on your homework out in front of you. Maybe take a screenshot of this or something so you have it in front of you when you're doing your homework, which of course everyone's doing their homework. So let's take an example. My population function. This could be a description of what my bank account is doing, what viruses are doing, what animals out on the Sahara are doing. Population growth, interest growth, all that kind of stuff. 300 times 1.05 to the t. Okay? So the initial population is 300. And what's the growth rate? Well, this is 300 times 1 plus r to the t. And 1 plus r is equal to 1.05. Subtract 1 from both sides, and we get r equals 0.05. Of course, this is the growth rate. Okay? And it's greater than 0. So that means this is exponential growth. How would you get an example of exponential decay, Mark? Please tell me. I am so glad you asked that question. If it were 300 times 0.97 to the t, initial population still is this, but my growth rate, excuse me, there we go. 1 plus r is equal to 0.97. So if I subtract 1 from both sides to solve for r, I get negative 0.03. So this is how much we're losing each time. So I could write this as 300 times 1 minus 0.03. Oh, that looks like 2 decimal points, doesn't it? That doesn't seem right. There we go. Uh-oh, where's my pen? There it is. Where am I? Oh, there it is. So that's what this function really looks like. And r, as you can see, is less than 0. It's negative. And so when it's 0, when it's negative, then we have exponential decay, because this, a number smaller than 1, whenever I take a number smaller than 1 and I raise it to an exponent, it gets even smaller. So this is, because this is a number less than 1, that's decay. Okay? Okay. Okay, I have a function. Here's another example. With initial population of 43 and decay rate of 7.5%. So first of all, 7.5% is 0.075. And this is the decay rate, not the growth rate. If it was growth rate, if this was growth, then I would write that as plus 0.075. But because it's a decay rate, I'm going to think of it as negative 0.075. So my function is going to be P0, 45, times 1 minus 0.075 to the t. Decay rate, decay rate, decay rate. The word decay makes that a minus instead of a plus. So 1 minus, so we could simplify this. 45, 1 minus 0.075 is 0.925. So that's what this would look like, okay? All of these just getting used to the words. Okay, so a something or other has an initial mass of 15 grams. And it decreases by 4.6% per hour. Okay? Write the function. I'll let you figure this out. Pause it and try to write it. Ready, set, pause. Okay. So, let's see if we can figure this out. Oops. Our population function, whatever it is going to be the initial value times 1 plus r to the t. And it says decreases 4.6% is going to be 0.046. So this would be 15 times 1 minus 0.046 to the t. Because this is how much it decreases each time. And then we'd simplify this, whatever that is. Does this make sense? Okay. And if it said increases, you would make this a plus, right? Okay. This is a good one. This is number 22 from the book. Oh, this would make a good test question. Wow, this would be fun. Okay, so we got a graph. It says, here's a graph. And it goes zoop. And right here, the initial population is at 0.3. Oh, well, we got another point over here. It says it's at 1.49. So write the population function. Okay, well, this is going to be is P0 times 1 plus R to the T. We know what P0 is. What's the population at T equals 0? It's 3. So I can write this as 3 times 1 plus R to the T. And my nose itches. But now how do we do this? Well, let's put in the next point. So here's our population. 1.49 equals 3 times 1 plus R to the 4th. Okay, so this doesn't seem too terrible. So first I'm going to divide by 3 equals 1 plus R to the 4th. And that comes out to be, this is 0.497. Now, so I have 0.497 equals 1 plus R to the 4th. Now I got to take the 4th root of both sides. And the way I do that here is I do 0. Did I miss a number? No, I didn't. 0.497. I'm going to raise it to the 1/4 power, because 1/4 is the same as 4th root. So I'll do this on my calculator. 0.497 caret 1/4. Or you could do 0.497 caret 0.25. Then it will use that as an exponent. Or you could use the X to the Y button if you have one of these. And I think you would hit, it depends on your calculator. I think it's on mine, 497 X to the Y, 0.25. First number goes in for X, second number goes in for the exponent. I think that's how it is on my calculator. I never do this because I have the caret button and I'd just rather do that. So when we take the 4th root of this, what do we get? I don't know. I got to do it. I don't see it. Where's my calculator? In here. I gotta switch. No, I got the right glasses. So this would be 0.497 caret 0.25 kaboom. Okay, that becomes 0.84. And the 4th root's going to cancel the 4th power, and we get, I don't even need to do that, 1 plus R. Now I subtract 1 from both sides. I get negative 0.16 equals R. Now I can plug that into my function. This is exciting. 3 times 1 minus 0.16 to the T. So that would be, actually, this thing is what ends up going in the parentheses here. P sub T equals 3 times 0.84 T. Ta-da! Now that was fun. Okay, this is a common type of problem. Let me turn this thing off. That's a common type of problem in exponential growth things, is you have 2 points and you got to plug them in and figure out what the initial value and what the rate is. Very, very common. So these are relatively straightforward. There's problems to identify the graph. There's problems to write the right form based on the wording. There's problems to use the points in the graph to figure out what the rate is. Okay, I'll do some more example problems like that during office hours and the problem solving session. So if you need help, you should come and get help before the homework is due and before the quiz is due. So have fun, enjoy exponential growth and decay, and we'll see you next time.